Hello everyone, and welcome to today's chem lesson. Today we're going to talk about covalent bonds in more detail, looking at what makes them polar or nonpolar. Then we're also going to take a look at the overall molecule and see what makes it polar or nonpolar. But first we need to define polar and nonpolar. Polarity is all about electrons being shared equally or unequally. The hiccup is that a nonpolar bond, right, something that is nonpolar, has electrons shared equally. So it's a little bit the opposite of what you would expect, right? Polar has electrons not shared equally. Molecule or bond, that is what polar or nonpolar means, right? A nonpolar bond means that electrons are shared equally. A nonpolar molecule means electrons are shared equally. A polar bond means electrons are shared unequally. A polar molecule means electrons are not shared equally. Right? The word polar or nonpolar doesn't change definition when we're looking at bonds or molecules. But the way we identify if those electrons are shared equally or unequally changes if we're looking at bonds or molecules. For a bond, we want the same element on either side of the bond. These are the only nonpolar bonds. The same element connected. If you have any other element on the other side of a bond, you have a polar bond. The only way an atom can share electrons equally is if it is sharing with itself. There's nothing else that has the exact same pull on those electrons. And so there's only one way to tell. If the same thing is on either side of the bond, this bond is nonpolar. If there's different things on either side of the bond, this bond is polar. Diatomic molecules, diatomic meaning just two of the same element, right? Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. These 7 elements are at diatomic. They are diatomic when they are their simplest. You will never have just Br by itself. It will always be Br2. You will never have just O by itself. It will always be O2. You will never have Cl by itself. It will always be Cl2, and so on. These have nonpolar bonds because they are the same atom connected to each other. When we start looking at carbon chains also contain nonpolar bonds because there are carbon connected to carbon, carbon connected to carbon. So these here are nonpolar bonds. But once you add in something else, right, what happens if this connects to H's at the end here? These, because it is not a C connected to another C or an H connected to another H, these are polar bonds. The electrons in a nonpolar bond are shared equally, which means if we're looking at X bonded to X, the 2 electrons in this bond are exactly halfway between the 2 elements. one is not stronger than the other. There is a perfect 50-50 split on these electrons, a perfect halfway sharing. In a polar bond, the electrons are not shared equally. One of these elements has a stronger pull than the other. Because of that, the electrons are closer to one element than the other. So the sharing is anything but 50-50. It could be slightly closer to X than Y. It could be very close to X and very far from Y. And anything in between. Right? If we wanted to really get into it, it could be anything from slightly closer to one than the other, all the way up to almost ionic, almost transferred. Anything into this range is a possibility, as long as it is not a 50-50 split. Let's look at some examples and see if we could identify if the bonds in these molecules are polar or nonpolar. Looking at NH3, are the bonds in NH3 polar or nonpolar? A on the left, B on the right. The bonds in ammonia are polar bonds. These bonds all connect an N to an H. That is not the same thing, so it is a polar bond. Right, there are 3 polar bonds in this molecule. What about this molecule, CH4? Polar bonds or nonpolar bonds? Good. Again, we see a bond connecting 2 different elements. Right? There are 4 polar bonds in this molecule because C is not H. What about this molecule? CH3Cl. Are these bonds polar or nonpolar? Here, these are still polar bonds. We have C connected to H, which is a polar bond. We've got that 3 times. And we also have C connected to Cl, and C is not Cl. All right, so that is a polar bond as well. All four of these are polar bonds. What about the bond in H2? Is it polar or nonpolar? Great. This is a nonpolar bond. We have an element connected to another copy of that element. H connected to H, if I know how to draw H's correctly. H connected to H is a nonpolar bond. They are the same element. This is the only kind of bond that is nonpolar, is when you have the same thing on either side of the bond. HCl, polar bond or nonpolar bond? Wonderful. We know that this is a polar bond because H and Cl are not the same thing. So that's how we tell the difference between polar bonds and nonpolar bonds. Now let's take a look at molecules. Let's zoom out and talk about the molecule as a whole and how we can tell if that is polar or nonpolar. Polarity still means the same thing here. When we look at a molecule, we're still looking at, are the electrons shared equally or are the electrons shared unequally? But the way we determine this is very different. We're not just looking at the bond anymore. We're not just going to ask ourselves, are these the same thing? And so it's a nonpolar bond. Or are these different things? Therefore, a polar bond. When we look at molecule polarity, we're zooming out. We're not just focusing on one piece. We're not just focusing on one bond. We are focusing on the molecule as a whole. And when we focus on the molecule as a whole, what we're looking for is symmetry. When I draw carbon dioxide, it looks like this. If you remember from our previous video, right? We draw out our Lewis dot diagrams, we connect them together, every lonely electron gets a buddy, we end up with this picture. And I said before that these drawings are really important to do correctly. And this is why. Because if you draw it wrong, you get different symmetries. When we want a symmetrical molecule, what we want is two or more lines of symmetry. If you can draw multiple lines of symmetry in a Lewis dot diagram for a molecule, you know that the electrons in that molecule are spread out evenly. Right? Carbon dioxide has two lines of symmetry, one going horizontally through the whole molecule, and one going vertically through the carbon. And I hear it already, but Mr. M, that's not symmetrical. Carbon, the C, is not symmetrical vertically. You can't put a line of symmetry. You can't fold a C over itself in the vertical axis. That doesn't make any sense, right? This isn't correct. And I want to pause right there, right? Let you take a breath. This might not be symmetrical in the classical sense, right? We're not looking at folding half of a C over onto half of a C. But remember that these letters represent atoms. Atoms that have a spherical nucleus and shells going around them. And so just because the letter C doesn't have a line of symmetry in it, an atom is perfectly symmetrical through the top, or through the side, or through literally any angle, because it is a perfect sphere. So when we're looking at these lines of symmetries, I need you to remember that the element symbol represents a spherical atom. And that even though the letter might not be symmetrical, when we draw this line of symmetry, we are talking about half of a carbon atom on the left and half of a carbon atom on the right, and those are identical, even if the letter is not. Same thing goes for things like bromine. Right? If we draw a Br, bromine is not symmetrical in any way. Right? There's no classical line of symmetry in the letters B and R. But if you drew these two lines of symmetry representing the bromine atom, you would be correct. Because bromine, the atom, the top half and the bottom half are the same. The left half and the right half are the same. And so when we draw lines of symmetry, as long as you cut the letter in half and then fold everything else onto itself, right here we cut carbon in half and an oxygen folds over onto an oxygen. This is a line of symmetry. This is a line of symmetry. On the other hand, let's stick with red. An asymmetrical molecule is polar. Right? And that means 0 or just 1 line of symmetry. A single line of symmetry is not enough for a 3-dimensional molecule. And so when we look at something like water, which if we remember looks like this, and we draw lines of symmetry, we're only able to get one diagonally through the middle like this. This is a polar molecule. The electrons are not shared equally in this molecule. They bunch up somewhere in the molecule. Carbon dioxide is a nonpolar molecule because of those multiple lines of symmetry. These electrons are all shared equally. These electrons are not shared equally. These electrons are shared equally. These electrons are not shared equally. Just for consistency's sake, let's make that red. Right, the definition of polar versus nonpolar doesn't change. Polar still means unequally shared. Nonpolar still means equally shared. But the way we identify that changes whether we're looking at a bond or a molecule. For a bond, it just depends if there's the same thing or different things on either side of the bond. For the molecule, it's about these lines of symmetry. And if we take a closer look at all 5, 6 of these bonds, you'll notice that none of these bonds, right, these two in carbon dioxide, these two in carbon dioxide, these two in water, none of these bonds are nonpolar. All 6 of these are polar bonds, and that is fine. Having a nonpolar molecule does not mean you have nonpolar bonds. They are independent of each other. But overall, these electrons are spread out equally, even though within the bond itself, when you look at that zoomed in portion, these electrons are not shared equally. Let's take a look at some examples again and see if we can identify if the molecule is polar or nonpolar. Here we've got NH3. Is this molecule polar or nonpolar? Great. This is a polar molecule. We can only draw one line of symmetry in this molecule. Right? And forgive my not so straight lines, but we can only draw this vertical line of symmetry through this molecule. One line of symmetry, polar molecule. What about CH4? Polar molecule or nonpolar molecule? Great, there are a bunch of lines of symmetry here. We can draw the vertical, the horizontal, either of the diagonals. We can stop once we have 2, so whichever 2 you see first is totally fine. Right? As long as there are more than one line of symmetry in a molecule, it is nonpolar. The electrons in this molecule are shared equally overall, even though each of these bonds is polar. The molecule overall is nonpolar. What about CH3Cl? Is this a polar molecule or a nonpolar molecule? This is a polar molecule. There is only one line of symmetry we can draw, and it is this horizontal one through the center of these atoms. You cannot draw this line of symmetry. This line of symmetry is not a line of symmetry, because if I try to look at this half and compare it to this half, they're not the same. This half of an H is equal to this half of an H, so that's good. This half of a C is equal to this half of a C, that's good. This half of an H is equal to this half of an H, that's good. But then when we go to fold this chlorine onto this hydrogen, these are not the same. So this vertical line of symmetry does not actually exist here. Right? Half of a letter that is not symmetrical is fine, but trying to say that a chlorine and a hydrogen are the same is not fine. So this is the only present line of symmetry here. Right? We get the same reasoning for these half molecules, or sorry, half atoms, and then this H folds onto this H, which is fine. What about this molecule? H2, polar or nonpolar? H2 is a nonpolar molecule. We can draw this horizontal line of symmetry and also this vertical line of symmetry. Multiple lines of symmetry means we have a nonpolar molecule. What about HCl? This is a polar molecule, right? The only line of symmetry we can draw is this horizontal one through the molecule, cutting the H in half and the Cl in half. There is no other place for a line of symmetry that actually gives us symmetry. Now, I would like to summarize. And so I gotta find my blank page. Oh, which I don't have in here. Excuse me for 1 second. Let's get a blank page in here. Let's summarize this up. We've got two things, right? We've got polar, which doesn't start with a B, polar, and nonpolar. And we've got bonds and molecules. So let's take a look. What makes a bond polar? A bond is polar when there are two different things connecting it. X connected to Y. Any two different elements connected together makes a polar bond. this bond is polar. A nonpolar bond would be two of the same elements connected together. Two identical elements means that this bond is nonpolar. When we look at molecules, our focus changes. We zoom out and we look at the whole molecule overall. For a polar molecule, we are looking at 0 or 1 line of symmetry. So water is polar. This thing that has 0 lines of symmetry in it is polar. Right, we're looking for a molecule with 0 or 1 line of symmetry. This has 1, this has 0. There's no way to draw a line of symmetry through this thing. For a nonpolar molecule, we're looking at something that is symmetrical, something with multiple lines of symmetry. So any one of these molecules either of those two molecules, multiple lines of symmetry, and here I want to write this neater, more than 1. So for CH4, you can put the vertical, horizontal, and either diagonal. For something like Br2, you can get the vertical and the horizontal. Not really a diagonal option here. But anything that has multiple lines of symmetry is a nonpolar molecule. When we talk about polarity, we're talking about uneven electron sharing, no matter what it is. If it's a bond or a molecule, we're looking at uneven electron sharing. And for a nonpolar molecule, we're looking at even electron sharing. Again, whether it is a bond or a molecule, either one, these are evenly shared electrons. And with that, with this lovely summary under our belt, I am going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.